Thank you. So today I want to talk about the efforts uh, that incorporate portable infrared spectral imaging into planetary geological fieldwork. So the main objective of this study is to test the integration of portable infrared spectral imaging into the geological fieldwork. We think that spectral imaging could be helpful for future human missions and that it can also help in making strategic decisions in the context of predefined scientific objectives. So I like showing this image. There's a moon in the sky, and then the land at the bottom looks much like the surface of the moon. It's a basaltic rock. The point with this image is that we want to go to the moon in the sky and work there, collect samples. But before doing that, we want to stay on Earth and practice first at a land that looks much like the surface of the moon, or in other words, a terrestrial analog site. So the terrestrial analog site for us is Kilauea volcano in Hawaii. This is a good terrestrial analog site because the mineralogy and the landscape looks much like those on the moon and some differentiated asteroids. So the particular area that we study is within this red box. This is the December 1974 flow and its surroundings. So we go there to Kilauea and then characterize the rocks and other materials we see there using emission spectroscopy. Every object in the middle infrared, which is about 5 to 15 microns, is emitting light depending on the Planck black body radiation and emissivity. Emissivity is a property that describes how much light gets emitted by materials, and emissivity as a function of wavelength or emissivity spectrum is unique to different materials. So we can extract that and use that to identify the minerals, rocks, and other geological materials that we see at the field site. We don't have a particular instrument that was specifically designed to do this task. So we had to come up with our own and try to assemble in-house using the devices that were available to us. So with that, we have infrared imaging camera and some narrowband filters. The camera is a broadband thermal imaging camera made by company FLIR, which was made basically to get temperatures of the environment. We turned this into a spectroscopic instrument by combining with these narrowband filters. These filters were designed to transmit light in the wavelength range of, say, 8 to 12 microns. This is the range where a terrestrial atmospheric window is, and also this is the range for where a major spectral feature happened for silicate minerals. So we have 5 of these filters. We combine with the imaging camera and make a 5-band multispectral imager. We take that and go to our field site. This is one of the scenes right next to the December 1974 flow itself. Here we see several things. To the left, there are basaltic boulders. On the other side, we see some basaltic sediments. In the front, there are consolidated ash. And in the middle, I have set up calibration targets that I use for computing emissivity. And this is what the process image looks like. This is a decoration stretch image where I assign the colors red, green, and blue to the wavelengths 8.6, 9.1, and 11.3 microns. Decoration stretch image maximizes the spectral variabilities that we see within this scene and tries to put out an image that humans can recognize by just looking at it and then telling the difference in terms of colors. So with that, we see basaltic boulder in hot pink, and then consolidated ash is in turquoise. Basaltic sediment is kind of in peach or light pink color. We think that images like this is going to be helpful for planetary geological fieldwork. Say one example by using it as a guiding map. So astronauts may collect several samples from the pink unit and say, oh, I have collected several samples from here, so let's move on to the turquoise or some other area. Another way might be documentation. After sample collection, they can look at the images and try to assess the representativeness of the samples that they have collected. So for us, we also collected samples from this scene and then took the samples to the lab and collected more spectra. I plotted three spectra for the three units that I have identified here. And the spectrum for the basaltic boulder is in the red curve. The blue curve is basaltic or consolidated ash, and then basaltic sediment. And then the green curve is ash. The main point here is that these three units are distinct from each other spectrally, which is important because this lab measurement is serving as the ground truth to what we see with the imager, especially at 9.1 microns, where a major absorption band happens due to opaline silica, which is found as coatings on many of the rocks at Kilauea. Okay, so moving on to another location. This is to the east of where we were in the last slide. We see similar materials here. We have basaltic flow, some sediments, and vegetation because it was more eroded and weathered. And then decoration stretch image again. Sediments are in blue, basalt flows are in pink, vegetation, shadows, and other high emissivity areas are in green. Here I just want to focus on this sediment section. If you look close enough, you might see that there are mainly two types of sediments or sections of the sediments here. The top half is more light blue green, and then the bottom half is darker blue purple. What this is indicating is that these two sections of the sediments are distinct from each other spectrally. And that is important and might require further analysis by taking samples or using more different instruments. If you look at the same scene in just the naked eye, again, this is what we see. It's just a digital camera photograph. The difference between these two types of sediments is really hard to see just using the naked eye. Again, the line is here. If you look at this, close enough for a long period of time and maybe know the knowledge beforehand, then you might be able to tell the subtle differences between these two. But the point is not doing that here. Especially for astronauts, they want to get useful and important information quickly and as easy to read format as possible. So in that case, using this kind of normal, visible light is not going to be as helpful as the spectral image. So we went back to this site and after image processing and tried to see ourselves if the variabilities that we saw is actually true. So we went up very close to it and snapped a photograph that's shown in this top right image. And it turns out that if we get close enough, we can tell the difference between these two types of sediments just by looking at it. We also took samples and then collected spectra in the lab, and indeed they are different spectrally, especially at 9.1 microns. So that was a good ground truth. Now that we have seen some examples of how spectral imaging can be beneficial to geological fieldwork, we want to think about how to use this technique in terms of the whole sample collection process on another planetary surface. We thought about several workflows that incorporate spectral imaging, and here I'm just presenting one of them, which starts out by acquiring spectral images from a reconnaissance rover or a vehicle that the astronauts are in. The astronauts can prepare to go do extravehicular activity while that is happening, and by the time they are ready to go out, the images will also be ready, so they can upload the data on, say, a portable handheld device, and then take that, and while they are collecting samples, they can use the images as a guiding map. So this will serve as one of the factors that will drive the whole sample collection process and making decisions. And especially it will work in concert or together with inputs from other instruments like X-ray fluorescence. So after they collect samples, go back to the vehicles in the back room, they can still use the images for documentation, documenting different spatial relationships among the units. So with that, in conclusion, infrared spectral imaging more easily capture variabilities and really subtle variabilities within the scene much better than what humans can see with the naked eye in the visible light. And for that reason, infrared spectral imaging holds a potential to benefiting planetary geological fieldwork and science return in future human missions. And at the bottom, I'm showing a preview here. We recently acquired datasets from Panoramic Hyperspectral Imager. This is this has better and wider field of view and more spectral bands, better spectral resolution. So we are expecting an improved compositional distinction from this data set. And this is also at Kilauea, right next to the December 1974 flow. The data set is getting processed right now, so please stay tuned for its results. Finally, acknowledgments to my advisors and the field team from RISE. Thank you, that's the end. Please.
Yeah, this is cool. This was a cool talk.
Thank you.
How much of a role does the emission phase function play in all of this? Because you're obviously looking at surfaces that have different phase relationships to your viewpoint.
Right, yeah, that's actually a good question. We haven't really tried to analyze that yet. We are trying to do that right now by taking measurements in different angles. And there's actually a lot of factors that go into this. So phase is one of them. And there is also shadowing effects from the clouds. We are working with the best conditions possible right now. And ideally, we would like to take those into account. But at least for now, the variabilities that we see are maybe it's not true in terms of absolute emissivity, but they are relatively true and useful for distinguishing different compositions. So that's what we are working with right now.